Okay, so our speaker today is Joshua Heath. He's visiting from New Hampshire in the United States. So Joshua did his PhD in condensed matter theory in Boston College, and since then he's been working kind of at the intersection between condensed matter theory and quantum information theory in Dartmouth College. So today he's going to talk to us about one of the big topics in condensed matter theory, high temperature superconductors. So over to you, Joshua.
Thank you, Shane. So it's very nice to be here in Dias in Dublin. So today, Shane said, what we're talking about today is some work I did at Dartmouth College. At the moment, I'm a postdoc under Lucas Boyack, I'm a professor now, and we'll be talking about some universal electromagnetic properties of strongly coupled electron-phonon superconductors. And this is work that the paper has basically been written, but we're going to put on the archive sometime in summer. So the main point of this talk is really trying to understand some universal properties of superconductors, in particular superconductors that were first proposed to be the phenomenon that was seen in superconductors more higher temperature. So here what we can see for these different classes of superconductors, we have critical temperature Tc versus here. And superconductors were first discovered in early 1900s, 1911, and they were known to be a material that has zero resistivity and to be a perfect diamagnet, so a perfect portion of an external magnetic field. And the first example of this was mercury, as can be shown here. And then eventually more materials were discovered, lead, niobium, and so on. And these materials, these superconductors along this path, spin path, follow the theory of Bodine, Schaefer, and Cooper, BCS theory, which is a simple theory of Cooper pairing or electron pairing that leads to non-phenomenon that we see experimentally in superconductors. But the problem with BCS theory is that it really only has a high critical temperature Tc, where superconductivity emerges, of around 40 Kelvin and stuff, as you can see by this material in GB2. Now, around 1986, 1987, what was discovered were a different class of materials, the cuprates, which are denoted by these carbon-oxygen layers, that had a much higher transition temperature. And as I'll discuss later, they are now known to not follow BCS theory. Basically, we don't know what is the glue that's holding these electrons together in cuprates. And really, what this talk is going to try and understand is expanding upon this idea of one idea that was proposed for the cuprates, and to try and see how universal it is. And now, universality is important in all of physics, but it's particularly difficult here because all superconductors, high temperature superconductors, behave a little bit differently. So one researcher might try to define some universal property that would be applicable for like one class of cuprates, but then we would change like some specific in the material, and then that law would completely fall apart. So all these high temperature superconductors sort of behave a little bit differently. So
when we talk about universality, we typically tend to think of it mapping to a field theory.
Mm-hmm.
Well, are you saying the field theory for the cuprates is slightly different?
So the field theory for the cuprates, when I think of field theory, I might think of a G and Y model. So that's currently being developed. I think what's important in context of field
theory. The usual field theory for superconductivity is scalar electrodynamics.
Mm-hmm. Well, I think what's normally proposed now is like this modified such to be a Kitaev model with disorder, because the goal is to try and reproduce this like right above Tc, like a strange metal phase.
So I think that's what the high one, but that's probably not universal.
No, it's not. No. So I'm talking about like universal experimental signature. So I'll go into a little bit later what I mean by these universal. Good question. So normally, so universality is quite difficult. So as we had to deal with some difficult question, we must go to Russian literature for inspiration. So what has been proposed by Jorge Hirsch was this idea of the Anna-Karenina principle for high temperature superconductivity. So all conventional superconductors are alike, that is BCS superconductors, whereas all unconventional superconductors are unconventional in their own way. So all unconventional superconductors sort of behave a little bit differently, so it's really difficult to pin down universal behavior. So basically, Rufus and I oppose the Anna-Karenina principle. We propose, as I'll say in a second, a different principle to really understand much more universal behavior in a sense in these Kubrick superconductors and beyond. So instead of talking about Leo Tolstoy, we can talk about a different famous literary figure in a second. But basically, to try and pin down what I mean by universality, as a question before just addressed, is this idea of home scaling. So as I said before, there was a lot of debate about what do we mean by universality in these materials. And in 2004, there was an experimental work by Christopher Holmes, which actually pinned down some seemingly universal behavior that was applicable for all Kubrick superconductors. And what Holmes found experimentally was on the y-axis, he plotted the zero temperature superfluid density versus the normal state conductivity times the critical temperature, and he found a linear scale relationship. And it was independent of doping level, it was independent of the material used, it was independent of the impurity concentration or the material specifics. So what's important about this is that whereas other people were trying to propose this universal, trying to pin down universal features in the Kubricks, in these high temperature superconductors, and weren't able to, Holmes found it seems to strike gold in a sense by just plotting zero temperature superfluid density by normal state sigma dc times dc. So a zero temperature ground state property on a y-axis, and basically a normal state property on x-axis, and a completely linear scalar relationship. But the problem was that this is really more universal in the Kubricks. Well, not really a problem, but as I'll explain in a second, but it was found that it didn't just work for the Kubricks, it also worked for the pnictides, the polylenes, elementals, the organics, even worked for lead and niobium, and all of these different materials fell upon Holmes' line. So the question now we want to ask now, so Holmes scaling, this linear relationship was really proposed as a signature for high TC superconductors, but now we've seen actually that's much more universal than that. It's much more universal than just high TC, it also works for low TC systems. So it seems to be something that's working for both BCS superconductors and unconventional superconductors. So it begs the question of what's really happening here. So Rufus and I, on my proposal, is that Holmes scaling is actually a byproduct of non-Galilean invariance and underlying microscopic level. It has nothing to do with TC or the underlying pairing mechanism, or if it's high TC or low TC, or has a high impurity concentration, a low impurity concentration, and so on. And the way we're going to do this is actually not considering BCS theory, we're not going to be considering high TC, we're actually going to be considering something else, something called Eliashberg theory, which is basically a numerical theory of superconductivity, which takes into the full effect of electron-phonon interactions. And we'll be doing this at arbitrary impurity concentrations. So I'll be talking about dirty and clean superconductors. Dirty means that basically the mean free path is very small, so the transport scattering time is very small, whereas a clean system has a diverging transport scattering time, as I'll show in a second. So we'll deal with dirty and clean systems. And what this implies now is that these universal features of electron-phonon superconductors will basically find Holmes scale in the Eliashberg system. And this changes colloquial notions of what we know as conventional superconductors. Actually, we'll show that one class of BCS superconductors actually doesn't obey Holmes scaling. So we really have to redefine what we mean by conventional. So instead of going to Leo Tolstoy, we can go to Vladimir Nabokov, another famous Russian author, and we can develop our own principle, the Ivan Wien principle, after his the first sentence of Vladimir Nabokov's novel Ada or Adora, which is sort of pokes fun at Leo Tolstoy. We say all Galilean invariant superconductors are more or less dissimilar, and all Galilean non-invariant superconductors are more or less alike. So what do we mean by this? Basically, this idea that Holmes scaling the Home scaling unifies nearly all non-Galilean invariant electron-phonon superconductors. And this really redefines what we mean by conventionality. So this is a law that's applicable to this Home scaling law, which is equivalent to non-Galilean invariance. It's applicable to the dirty BCS system, the electron-phonon superconducting system, the high-temperature superconducting system, and so on. So before I continue, any questions? Yes.
Yeah, the scaling, the linear scaling is on log scale, right?
Yes.
So does the if you make it to linear scale again, it becomes a power law, I guess.
Okay, so that's a good question. So if you experimentally, what we will find is that it still follows some linear scaling because it's log log. It's still linear, but it's more spread out. Now, so it's not perfectly underlined. As I'll show in a second, if one considers the BCS system, then you can consider like what knob are you tuning theoretically to get its linear scaling. It's the transport scattering time tau, and then you see perfect linear. And we'll see that again theoretically in the electron-phonon system by tuning the electron-phonon coupling strength.
So you're saying slope of the line was 1?
The slope of the line, it depends upon what units you take. I think it was taken to be.
Well, then log it shouldn't.
I can go back and see.
Logs are dimensionless.
I don't recall the actual.
Only log will give you linear and you exponentiate it. That's just the coefficient.
Yeah, I don't recall the exact value of the slope in this context. So we actually take a different convention at experimental work. We take a definition of the Home slope, which is, as I showed you, which is unitless, divided by the plasma frequency squared. These guys took it in somewhat different units that were more convenient experimentally. So I can return to this later. Yeah.
What do you mean by Galilean invariance or non-Galilean invariance at this point?
Okay, so maybe I can talk about it briefly now. So basically, if I have like a very dirty system, like a system of high impurities, if I do, that will have a small mean free path. So if I do a Galilean boost to momentum space, the physics will look different than due to the small transport scattering time. However, if I have a clean system, then the mean free path is divergent. So if I do a Galilean boost, everything will look the same. So basically, a dirty system, like a dirty superconductor, will break Galilean invariance, while a clean system will not. And what we'll find basically is that we have similar notions of Galilean versus non-Galilean invariance due to very, very strong electron-phonon coupling. So that's what I mean by Galilean versus non-Galilean invariance.
And how long has this terminology been used in superconducting physics?
So this idea of Galilean versus non-Galilean invariance really came to precedence. I think one big work was very recently, 2023, Chupakov first proposed this idea, as I'll discuss momentarily, also in the context of Eliashberg theory, on how Galilean versus non-Galilean invariance affects superfluid density.
And there's good experimental evidence for what you see.
Well, I believe there should be some connection, experimental connection in Chupakov's work, but I had to double check. Yes, did that answer your question before?
Yeah, actually, follow-up was.
Okay, follow-up question did, yeah.
But yeah, it should be. It looks very much like a slope on there, and that would mean it's still linear, even if you're on a linear scale.
I see. Yeah. Okay. Yeah, we can go back to that later. But yeah, the experimental work in general use much different units than we're dealing with. So we'll be dealing with units, the Home slope in these dimensionless units, basically. Okay, good. So first, let's go over the first part, which is unconventional superconductivity. So first, I'll go over some more implications of Home scaling itself before going into Eliashberg theory, depending upon time. So first, some of these ideas to get into the main portion of the talk is this idea of E&M for conventional superconductors. So basically, I'll go over what I said before, but a little bit more detail. So as I said before, conventional superconductivity basically was proposed by BCS in 1957, and of course was started by the London equations by London and London in 1935. And basically this idea is that conventional superconductor means that we have perfect diamagnetism, and it is a perfect conductor, so basically zero resistivity. Now, what's important for our work, as I'll show in a minute, is to follow work by one of Bardeen, the Bean BCS, Spratsky and Sambunal, who proposed in 1967 that the condition for diamagnetism is equivalent to the condition for zero resistivity. So these two conditions were basically equivalent. So basically, if we can define the current density in this form, when we use some Cartesian coordinate, then there are these two different limits for the kernel in the current density, whereas Q goes to 0 versus nu goes to 0. One determines the condition for non-zero superfluid density, and one condition determines the condition for zero perfect diamagnetism. And what I showed was that these two are equivalent. Then this basically is connected to, well, one implication of this is that it leads to a connection between the Bell and imaginary conductivities in a superconducting state.
What is the difference between those limits is the order in which you take them, is it?
Yes. So Q goes to 0 first, and then nu goes to 0, the frequency, and then the other one, nu goes to 0 first, and then Q goes to 0.
What is K?
K
You've got
is,
a 2 index K and you've got a 0 index K.
so K is the response function. So it's electromagnetic response.
K is what?
K is the electromagnetic response.
That's K mu nu, but what is K?
Oh, so sorry, K mu nu is just shorthand notation. Sorry, K is just shorthand notation for K mu nu. So,
And your two variables, Q and nu, are no longer x and x prime, because it's symmetrical.
so I did a Fourier transform, sorry. So maybe this is somewhat confusing notation, but if I take a Fourier transform and I just have in terms of the frequency and the momentum, then whether or not I take one to 0 first and then the other to 0 would determine the penetration depth
So
versus
one of
the,
the variables is time for your transform.
yes, yes,
So it's a completely different notation.
yes, yes,
So K mu nu is a function of the difference.
yes. Okay, sorry. But the point here is that one condition for this that follows from this work is that the superfluid density at some temperature T is equal to pi tau delta T hyperbolic tangent of delta over 2T. So in the zero temperature limit, the superfluid density at T equals 0 is equal to pi tau delta. So there's a direct linear relationship between superfluid density and the zero temperature gap. So basically, even in BCS theory, we start to see there's a connection between the superfluid density and normal state DC conductivity.
So can you define the terms again? NS is the...
So NS over N is the superfluid density. So it's a concentration of Hooker pairs in the system.
Yes, and what is N without the NS?
N is just the normal density. It's the total density.
And you're
Yes.
assuming that the normal density is temperature independent.
Yes. Yes, so basically this is some number, is the number of the Cooper pairs. So in a perfectly clean BCS system, this will become 1. So this relationship will only hold in a dirty system. It's pi tau delta. So the superfluid density is suppressed in a very dirty BCS superconductor.
So it's the pair density.
Yes, so it's a pair, it's the density of the Cooper pairs. Yes. So it's connected to the transport scattering time, a normal state property, and the zero temperature gap. And as I said before, the problem with this idea, so we have this good idea of BCS superconductivity now, but the problem is unconventionality is the norm, really. A lot of superconductors don't follow this BCS line. The cuprates, the nictides, and the high pressure superconductors will be focusing on the cuprates specifically. But unconventionality is the norm, so we really have to expand and understand what we mean by unconventionality.
So what are you defining as the PCS line?
Sorry. So this green line here. So lead, iodium, MGB2. And these blue diamonds are the cuprates. So the highest temperatures may be at not only the high pressure, maybe about 140 Kelvin, 141.
So the green curve is the high and low temperature one.
Sorry, the green curve is the BCS low temperature. And the light blue diamonds are the higher temperature cuprates.
And there are some green dots which are way below that.
Yeah, so this is the BCS superconductor 33 gigapascals, and this is not an ambient pressure.
It's not A.
Ambient pressure, so it's a higher pressure superconductor, so no more
And the other green dot below the line?
So
Just up further, straight up.
It's star, I think. No, rectangular star.
It's, yeah.
oh yeah, that one is that
Rubidium.
that one, oh yeah. That is also should follow some BCS theory of context. That's a low temperature system. That's 22 Kelvin.
There doesn't seem to be any real trend associated with the BCS.
No, so not really. I mean, in general, BCS superconductors usually obey critical temperature below 22 Kelvin. There's a theory by Macmillan that talks about how TC should be bounded by the characteristic phonon frequency. And it was proposed that it should be lower than 22 Kelvin in BCS theory. But then MGB2 sort of broke that to be 40 Kelvin, but we haven't found any system that's above 40 Kelvin that's BCS. But the cuprates can go much higher, right? Like 100 Kelvin higher.
Yeah, actually, I'm confused.
So,
it's against year, which doesn't mean any physical meaning.
There's no expected nice.
There's no trend that I should be able to
yeah.
We expect it to go up, hopefully.
No, so yes, it seems to have truncated around 1994 or so. Unless you've got high pressure. Yeah.
All of these couplet ones obey that law that you gave in terms of a delta T with a tanh.
So the BCS
these green ones.
in the dirty limit. If I have a high impurity concentration, if I have a low impurity concentration and a clean, the superfluid density is 1, always. So all the green ones in a dirty limit obey that relationship that I write on the board, the NAT relationship. And so the n at equals 0 is prime out delta.
And what does dirty limit mean here for these objects? It means you put in some other jump into the system, is that what it means?
It means I have some kind of imperfect lattice structure, some imperfection of lattice that I characterize as like impurity dirt. Dirty, yeah. You got a question?
Just one, since we're on this figure again anyway. All the ones with the stars, they start off with these very low temperatures of uranium compounds. I guess they're included because then recently there was a high temperature version of those suddenly.
Oh, yes, uranium compounds interesting. Uranium germanium-2, I know, gained some interest because it's a ferromagnetic superconductor. And there are some ideas such that basically the theory is that a ferromagnetic superconductor should be perfect. It should be very high temperature because I think there was an old theory that suggests that ferromagnetism might help superconductivity, but actually not always very low. And it might be related to heavy fermion physics, but I'm not entirely, don't know exactly recall. Any other questions? Okay. So let's go over quickly why the cuprates are special. So the first idea is this idea of locality by Basshoff and Triplecoff in 2011. So basically, this is sort of like a hand-wavy argument, but it seems to sort of work for understanding these cuprates as opposed to BCS. So we can define RK roughly as the ratio of the experimental kinetic energy to some, say, non-interacting kinetic energy one might get from LDA or EFT, like band structure calculations. And in BCS theory, this RK is equal to 1, while in the cuprates it's much lower. So basically what this would suggest is that in the cuprates there's roughly a balance between attenuancy and localization. So instead of having very, very strong correlations that would lead to complete localization, like in an insulator, that instead it seems to be a balance in these cuprate systems, these high temperature superconductors. Once again, this isn't very aggressive, this is just some hand with the often notified asymptotically, which seems to work. Critically, what was noted by Van der Waal et al. In 2003 was due to some experimental measurements on a specific cuprate material, there seems to be quantum critical behavior in superconductors, and therefore the dissipation mechanism or diffusion mechanism around is driven by interactions. Homogeneity seems also to be important for these systems. So in the context of SPM measurements, the gap, the other electromagnetic properties seem to have a local structure, so it's not uniform across the lattice. And similarly, what I want to really more focus on as opposed to the first theory is this idea of normal state. So, and this would be also important to understand home scaling as well. So basically, first spearheaded by Baum in 1996, was right above the critical temperature Tc to transport properties in a normal state, or found to not be explained by non-Galilean liquid theory, sort of conventional theory of particles. And basically, in all these cuprates, right above Tc, something called a strange metal emerges. So in a strange metal, right above Tc, we can see here a plot of the temperature of this doping for some example material. And we see right above the superconducting dome, we have a strange metal phase. So the strange metal, basically in a normal metal, the electrons still behave like the electrons in a free Fermi gas, but just now dressed, quote unquote, by the interactions. Whereas in the strange metal phase, electrons don't really behave like individual particles anymore. They behave, the whole system behaves like a very strongly correlated quantum plasma. So we really lose individual particle characteristics, so on. And this leads to a breakdown of one famous law in Fermi theory, that resistivity goes T squared. In the strange metal, resistivity goes linear with T. So basically, this Fermi liquid property breaks down.
Sorry?
Yes.
You have a semicircular
Yes.
curve of phase transitions. What is the nature of the phase transition across that curve?
So you mean like the critical distance?
You're saying it's second order for all the curve.
I'm not completely certain. The point of the curve, I mean, the phase transition is still upward. The nature of the phase transition is still under study. What's interesting about this is that the dynamical critical instrument is not one, it's multi-sonic, I think it's 4/3. And you now have hyperscaling violations as well.
So you know it's a second order transition.
Yes.
Is it second order for the entire curve?
I'm not completely sure at lower level.
Between the Fermi liquid and the superconductor?
I believe it is.
And between the strange metal and superconductor?
I believe so. I believe it
If
is.
you have your critical exponents, it will be.
Yes.
Whether they're dynamical or otherwise.
Yes. I think the point though is that, yeah, so basically at optimal doping, where the Tc is highest, there is the strange metal phase. What happens now in terms of what goes beyond Tc, in terms of like what's going on in the superconducting phase, is still under study, so we really don't know yet. So most people are focused on just what's in the strange metal phase itself, as opposed to what's happening below in the superconducting phase or along the critical line, specifically now.
And the dimension of the system?
Usually 2D or quasi 2D.
So you're just sticking with the 2D systems because the standard
Experimentally
was three-dimensional systems.
I mean, experimentally, normally in a quasi 2D, I believe, or 2D.
For some place along this curve.
I think normally when people, I mean experimentally, normally people deal with like 2D or quasi 2D materials, I believe. So normally I think people try to do 2D or quasi 2D theories.
For BCS theories, for 3D?
No, I mean for the high temperature cuprate modeling, like what?
Okay.
Yeah.
So this is a two-dimensional
Material.
phase diagram.
Yeah. Any other questions? Then I can go to specifics such as strange metal.
So you're saying the layers do not really interact?
Might weakly interact, so you might have quasi 2D, but normally it's pretty much non-tracking. Okay. So maybe quickly what's strange about the strange metal. As I said, there's no quasi-particles. So basically the electrons in the Fermi liquid will become dressed. So we have these quasi-particles. Well, now we have no consistent quasi-particle picture. As I just mentioned before, we have non-trivial criticality. This appears in the transport quantities. This order randomness is also important. So this linear T-resistivity is explained by 3D fermions coupled to quantum critical scalars. And as I mentioned in the first part of this talk, this idea of strange metal physics really led to this idea of universal scaling. So basically all proof rates exhibit this linear scaling relationship between superfluid density and sigma Tc, where sigma is the critical, is the DC conductivity at T equals Tc in the strange metal phase. Now the problem here is that this isn't really unique to the Coop ring. So we've been saying before, so where are we now? We talked about how home scaling was proposed as this universal thing for the Coop rates to try and give us this hallmark of high temperature superconductivity by connecting this very exotic property to superconducting system as high Tc to some unique property of the normal state, the strange metal phase. And we found this linear scaling relationship between superfluid density and sigma Tc. But the thing is that, as I hinted in the beginning, home scaling is more universal than high Tc physics. So in this plot, I'm actually plotting the zero temperature superfluid density over sigma Tc versus for a BCS superconductor. And I just found this numerically. So basically, this color corresponds to 1 over tau delta, and tau is the transport scattering time, and delta naught is the zero temperature gap. And what we see here is that we have linear scaling in the dirty regime, where tau is very small. In the blue regime, it's 1 over tau is very big. And then around here, in the cleaner regime, the green, it goes to 1. So even in the, as I said before, in a dirty BCS system, home scaling seems to apply. And in fact, this follows from Sung-Bo-Nam's work. So if we have pi tau delta naught.
Can you show that picture again?
Sure.
Because I don't understand.
Sure.
Because, so now you're dividing by omega p
Yes.
squared.
So-
That's the point, is it?
So omega p squared, the plasma frequency squared, just puts it in uniless form. And e pi squared is just a convention we took because it made the equation later on look better.
So that's not the point. So that's just a scale. That's
Yes.
nothing to do. So you're saying that the vertical scale now is different.
So the vertical scale is just 0 T superfluid density. What's different from the equation I showed before, the plot I showed before, is that this is BCS. This is a low TC system. This is not high TC. This is not Coop rate. So what's different now is that this is just a conventional superconductor. So home scaling in homes was proposed that, oh, we have this linear scaling between 0 temperature superfluid density and sigma Tc, and this is a hallmark, this is a smoking gun for high Tc physics. But this is a BCS system, and BCS is low Tc superconductor. And we actually can see this from Sung-Bo-Nam's work. So we rewrite pi tau delta. So sigma is just omega p squared over 4 pi tau. So we rewrite this as tau over, we write this proportional to sigma delta naught Tc over Tc. So I'm multiplying divided by Tc. In BCS theory, delta naught over Tc is a constant given by about 1.76. So that means this is some constant, we can call it capital A for now, sigma Tc. So home scaling works in a dirty BCS system from Sung-Bo-Nam's work. So there's really nothing particular about home scaling for the high TC system. So that's fact 1. Fact 2, in the BCS, home scaling only works in a dirty limit and by definition a recoupling limit. Now, what I want to stress here that's interesting is that BCS home scaling cannot explain what we see in the Coop rates. So, the Coop rates, what I just showed you before in Holmes' original work, Holmes showed that you have this linear scaling relationship for, first of all, the Coop rate systems, which are normally very more strongly correlated. They have more complex, whereas in the BCS system, it's a more weakly coupled system. Similarly, in that original diagram I showed for Holmes scaling, that Holmes reproduced, was not used in a clean limit. So in that experimental plot I showed, everything was in a clean limit of these superconductors. Whereas in a BCS system, Holmes scaling only works in a dirty limit. It breaks down the clean limit. So this leads to a problem in trying to rectify what's actually happening in with Holmes scaling, what it's trying to tell us. So the proposal, as I said before, is that Holmes scaling is more universal than BCS and Coop rate physics. And to give the goal now is to give us another physical knob to tune beyond just normal BCS theory, and that will be in its dynamical electron-phonon coupling in Eliashberg theory. So, any questions now? Okay. Yeah.
Just checking that I still understand. So
Yes.
you can theoretically actually show that this non-home scaling works for BCS.
Yes.
For BCS superconductors, yeah, exactly. But presumably you can't actually show this theoretically for the Cuperts. There is an observation.
Yes. So the Coop rate's a problem. There is no theory for the high temperature. I mean, there's a bunch of theories for the strange level, right? But there is no theory for high TC.
Yeah.
So we really have no theory. I mean, theoretical work on home scaling is limited to a holographic work from the mid-2000s, and I think some RG analysis. But other than that, this work I did with Rufus is the first.
Okay.
It's also the first work that deals with scaling in general in Eliashberg theory. So basically, it's this idea. BCS theory doesn't give us another knob to tune beyond tau. We need another knob to tune. And Eliashberg theory, which is a step beyond BCS theory, gives us this knob. So I'm not going to go into, I'm running a little bit late, so I might not go into the full derivation of Eliashberg theory, but we can deal with it very, do some mathematics first, actually. So, if I have some lattice, first of all, this little cartoon isn't from me. I should give credit where credit is due. This is due to my grand advisor, Frank Marsiglia, University of Alberta. This is his little picture that we all use. So, if I have some lattice, an electron comes in. Now, this lattice has positively charged ions, and the ions are going to be attracted to the electron and form a net positive charge. And this electron will be attracted to the net positive charge, right? But the problem is that the electron is mobile, it's going to move away, and then the ions are heavy. They're heavier than the electron, they're sluggish, and they're not going to bounce back fast enough. And there'll still be a net positive charge cloud here that the electron is moving towards, even if the other electron is moved away. So basically, this idea of Eliashberg theory extends BCS theory by incorporating these lattice effects in. It incorporates what's known as a dynamical gap, and it makes the gap frequency dependent. So like I said, I had to go a little bit faster here so we can go through the Holmes work. But basically, Eliashberg theory extends BCS theory by, instead of considering a constant excitation gap delta, we'll have a frequency-dependent gap in addition to something that's known as a renormalization Z, which is connected to the mass renormalization. These will be the two important factors here. And this factor Z will also be important for Holmes scaling as well.
So this is your Hamiltonian. So where is it going to enter? The gap is entering into V, is it?
Yes. So like I said, so this is just an extension that just shows schematically where it comes from. So basically, in the context of a BCS theory, we'd ignore the effect from the phonons, the A terms. We would just consider this for the Hamiltonian, right? Well, now in the Eliashberg theory, we include the coupling between the electrons and the phonons in the lattice. So we define Z in time here as the odd and even parts of the normal self-energy.
So it's, you put the pair forming in by hand.
Yes.
Yeah.
Yes.
So there's no explanation there. Of the actual pair forming.
Well, the pair forming it's still Cooper pair.
Yes.
Yeah, it's
By hand.
yeah, it's still Cooper pair, but it's now including this dynamical effect, basically. It is including more strong coupling effects from the electron-phonon coupling. But yes, it's still basic, still the same philosophy of putting in the gap by hand, yes. So now I'm going to go through this. Let me just go through these and skip these. Yes, sorry.
We don't tend to work with an hour, so just to work.
Oh,
We tend to be a little bit more relaxed.
okay. So,
Rushing through, I don't think is.
Yeah, take your time.
okay. Yeah, I thought I was cut off at 3. Okay, 3:30. Okay, that's fine. So basically, what comes at the end when these gap equations that determine delta and Z. So delta.
So just so I can follow, how was, I mean, you defined Z and chi there very rapidly.
Yeah.
And they were defined in terms of something like sigma,
Sorry.
but I didn't see how sigma was defined.
So sigma is the electronic self-energy. So
So
just
you're looking at the propagator,
yes,
and you're looking at the inverse propagator, and you're talking about the inverse propagator has a standard dispersion part and a self-energy part.
yes. So it's input. Yeah.
Self-energy.
Yes, and yes, inverse propagator subtract the non-tracting inverse propagator, the self-energy from the Dyson equation. Correct.
You're now splitting.
Yes.
Saying that is this omega times 1 minus z meant to be the inverse propagator, or have you dropped some part?
I believe so. No, this part is just the
You're defining z through the
yeah, defining Z and apply to the odd and even parts. Sorry, yes. Yes, I'm still dealing with quasi-particles. So everything I'm doing with Eliashberg theory is not applicable to high TC. So I'm still dealing with regular like quasi-particle picture. So Eliashberg theory it fails completely to describe high TC systems. And that's why it's useful for us, because we want to consider a system that might have home scaling, but it's not a high TC system, and it's not a BCS system. And that's why we want to go to Eliashberg. So it's still a quasi-particle, yes. So, with no approximation, the Eliashberg equations are given as such. So these are self-consistent equations defined in terms of these sums of the Matsubar frequencies. So we have a self-consistent equation for Z, for chi, and phi, which is related to the gap, Z times the gap. As I said, the order parameter phi. The coupling strength is defined by lambda, where alpha squared F here is the phonon propagator. We can simplify all of these significantly by assuming particle hole symmetry. So chi is 0. We have a local theory, so there's no K dependence, and there's no Coulomb repulsion. So all of these equations are simplified in this. So these are the simplified Eliashberg equations we'll be dealing with. So in general, the sum of the Matsubar terms goes from negative infinity to infinity. I would hold it here as negative m to n subtract 1 because I often deal with numerics, so we had to truncate m. And taking from negative m to m subtract 1 ensures that the Matsubar term is symmetric about little m equals 0 term. So once again, particle symmetry, local approximation, I'm considering only one band. And specifically, we'll be dealing with an Einstein model with some coupling lambda. So basically, the phonon propagator is some simple delta function at the Einstein frequency. So lambda here is just going to be equivalent to lambda with no argument. times Einstein frequency squared over Einstein frequency squared plus nu squared. And here in my notation, I'll basically look at weak strong or asymptotically strong Eliashberg. Now, weak Eliashberg, lambda is smaller than or equal to 0.5. This is from Marsigno's work. He did numerical work and has a theory for weak Eliashberg. And he found that the theory for weak Eliashberg theory breaks down when lambda is larger than 0.5 or so. I'm defining strong Eliashberg theory to be lambda larger than 4, and the reason I'll explain in a second. And asymptotically strong is lambda going to infinity. Lambda can also be defined in this way, which is alpha squared over omega e squared, where alpha is just a unit for electron-phonon strength. So lambda is unitless. So it's a number, basically. Lambda going to 0 basically should give you the BCS theory, but it has some complications that I'll explain in a second. So we can see here, it's a little thing here, a plot like numerically solving these equations from lambda equals 0.3 to 100. So about the point where the maximum of this curve, so this is a curve of delta n, the gap, versus the Matsubar frequency omega n. And when and we see for any lambda, it basically has this Lorentzian-like structure for Einstein model. So when lambda, when the top of the delta is about 1, then lambda is about 4. So that means that basically these units, delta is unitless. So delta, defining delta here is delta divided by omega e. So that means that the maximum gap is about equal to the characteristic phonon frequency. So that's why I'm defining that as a strong Eliashberg. Other people have defined it as lambda larger than 1. For realistic material, lambda is usually limited to 3.7 for the hydrides, but theoretically there's been a lot of work, as I'll show, for asymptotically strong, which is lambda going to infinity. Here Z basically follows the same form, except now, actually, for small lambda, it goes as 1.1. For small lambda, it should go as 1 plus lambda, and for as the maximum. And for the higher lambda, it should go as 1 plus square root lambda as a function of lambda. But also as a Lorentzian structure.
Just set the reference right. Z is equal to 0 for BCS.
Sorry. So BCS theory, delta constant, Z is equal to 1.
It's 1.
Come on. So you can see that here.
It's the impact to 0.
Yes. So now here we can actually see for very strong lambda, so first of all, it's a frequency dependence. If I go to the smaller lambda, so the blue, this is flat at 1. Well now, if I increase lambda, it actually gets quite large.
But you're saying that it goes like a square root of the large factor, that doesn't look like it, because the two scales are both in there.
No, because I'm not plotting it versus lambda now. So if I plot it versus lambda, so if lambda is small, so let's say smaller than 4, smaller than 10, let's say. Then Z goes as 1 plus square root lambda. The Z of the 0 Matsubar, so the top.
To look at the colors, not at the scale.
Yeah, so the color's not in this. And then for lambda going to infinity, Z0 goes as 1 plus lambda. Sorry, I knew other way around. Sorry. So this one, it goes to infinity, it goes 1 plus lambda, square root lambda. And because lambda is smaller than 10 or so, small, then it goes 1 plus lambda. Yes. Got it. Yeah. Good.
The one is, the one in the large one is irrelevant.
Yeah, sure. Yeah. Yes. So, however, lambda around 20, you start to see the 1 plus square root lambda behavior. Okay. Now, we can solve for TC for this by setting the delta equal to 0, and then we find TC from the Eliashberg equations numerically. What's often not discussed in the literature is that Combusco actually has, Roland Combusco in 1989, solved for an approximate form for TC in the Einstein model. And he found that TC over omega E is 1 over A square root E2 over lambda subtract 1. A is about 3.9 or so.
And what does an Einstein model mean?
Einstein model just means it's a simple phonon model with a phonon propagator. The spectral function is a delta function behavior. So it's omega subtract omega E, single frequency. So we also call the Holstein model as well. So in this Einstein model, this very simple model, well, now, and this is useful in Eliashberg theory because now we can just parameterize the electron-phonon coupling strength by the number lambda. So Combusco's Einstein model simplified TC to have this form, and actually you can see if we plot TC versus lambda, the blue is analytical from Combusco and the red is numerical from mine, and we see that it's completely overlapped. So TC goes to square root lambda. So TC in Eliashberg theory is unbounded, and what's interesting is that delta naught over TC, which I said previously for BCS theory to be constant, is now no longer a constant for Eliashberg theory. And there's experimental agreement for this as well, where we can see now, here we plot true delta over TC versus TC for these different materials. And the dark dashed line is Eliashberg prediction, and we see pretty much perfect agreement for this.
Is this the green line that you were drawing in the first place?
Which green line side?
In the first picture you had, connecting on the BCS disk.
No, that was just TC versus year. That was just showing the discovery of the material. So that was something different. So, just showing this briefly. So, as I said before, there's two limits to Eliashberg theory that we can use to better understand our eventual Holmes discussion. So one is the weak Eliashberg theory, and basically Lucasen in his conductivity book suggested that Eliashberg theory can produce BCS theory by imposing a hard frequency cutoff. Now it's also going to be the gap equation, reducing to the BCS result. But Frank Marsiglio proposed that lambda going to 0 should also produce the BCS result. And he found out in slight corrections. One is that the TC for Eliashberg as lambda goes to 0 is actually has necessary massive normalization. E subtract e to negative 1 from square root E. So it's a slight modification from the BCS result. Similarly, delta, the 0 temperature gap, at the 0 multiplier frequency is slightly modified over the BCS result, and there's some residual frequency dependence as well.
What is E supposed to be? The E supposed to be here?
E is an actual E as in 2.0.
Oh, is
Yeah, sorry. So this is a number.
Those keys are the same.
Yes, both these are the same. And delta over TC and weak Eliashberg theory remains a constant at the BCS value. So we don't get BCS theory exactly in a slight modification. But a strong asymptotic limit is where things become a little more interesting. So take lambda going to infinity, what happens to the Eliashberg equations? So we can basically rescale the Eliashberg equations by this form. So Q here is a scanning force variable, and I define Q bar here is Q over omega E squared lambda over 2. So in this context, I can define lambda as 2A over omega E. In an Einstein model, the spectral function is basically a delta function, where A is the weight of the delta function. Now, for lambda going to infinity, I can keep A a constant, and I can completely let omega E go into 0. So I can rewrite the Eliashberg equations for lambda going to infinity.
I'm confused. I don't see a Q bar or Q.
So Q is a standard, it's a variable. So it could mean omega or Z, or delta, excuse me. So Q's is available, that's all. So it's just a standard for something. It's a notation that combustible used, I believe. So we can define this bar notation, and in this context, an asymptotic limit where lambda goes to infinity, it's basically equivalent to an Einstein model, where lambda omega e is 1/2. And this is universal for any phonon model. One could consider some variation of the Einstein model for a finite lambda, and then take lambda going to infinity, and it's still described an Einstein model. And that's universal. What's also interesting is that we have this full description of in Eliashberg theory of dealing with real versus imaginary frequencies on a real or imaginary axis. And that can lead to a purely repulsive or purely attractive interaction depending upon whether or not on the real or imaginary axis itself. Similarly, Z goes to 1 plus square root lambda as lambda goes to infinity. This isn't that important. Basically, this is just showing the asymptotically strong Eliashberg theory phase diagram. We can define lambda as alpha squared over omega e squared. T over alpha versus omega e over alpha basically contains the entire spectrum of lambda for the Eliashberg theory. Okay, I do want to, how much, so I can go over, that's fine, okay. So let me just go over this very briefly because I do want to get to the home stuff. But basically, we can talk about this idea of electromagnetism again, and we produce some Bonham's work in the context of weak Eliashberg dirty theory. So remember, some Bonham's work led to this idea of home scaling in BCS dirty limit. And now we want to ask, in the simplest case of Eliashberg theory, that is in weak Eliashberg dirty limit, do we also obtain home scaling? And like I said, I'm not going to go over it. I go over this at the end if you're interested, but let me just flash through this quick. Basically, we can build off this by building off the work of Rufus-Boyack, who published his recent work on weak electron-phonon coupling as connected to NMR relaxation rate. So Mattis-Bardeen proposed that in the superconducting system, that we can split the conductivity into this real and imaginary frequency dependent part. And the real part at nu equals 0 is known as the new NMR relaxation rate, nuclear magnetic resonance, and nu times sigma 2 at nu equals 0 is the muon spin relaxation rate. So these two are connected from Primus-Kronig, sigma 1 and sigma 2. So then similarly, there's a relationship between a mu-SR relaxation rate and an inverse penetration depth in a superconductor, and therefore similarly the superfluid density. So what I'm saying here is that by building off of Rufus's work on the real part of the conductivity, we can immediately get insight into the imaginary part of the conductivity, and therefore the superfluid density, and then home scaling. For the simplest case that Rufus considered the weak Eliashberg dirty limit. Just flashing this briefly. Okay. So we can basically in a nutshell, we can consider two limits on the real axis of decoupling. The gap can be split into these similarly complex components. Sigma delta equals delta 1 plus I delta 2. And whether we take the total frequency nu, the external frequency nu, should be larger or smaller than the imaginary part of the gap, which is a technicality in the calculation. We always get the same equation. Pi delta 1, the real part of the gap, times the hyperbolic tangent, delta 1 over 2p. So this is analogous to some Bonham's result, and so we see as a first step that we really don't gain anything from Eliashberg theory at the first. So what it tells us is that Eliashberg theory reduces the BCS Holmes result in a weak dirty limit. So what we had to really do is we want to go to arbitrary tau and arbitrary lambda. So arbitrary tau means not going between weak and dirty, and arbitrary lambda, so not just limiting ourselves to weak Eliashberg, we want to consider strong, asymptotically strong, and so on. And we want to consider linear scaling, not just direct proportionality. And we want to consider general scaling relationships beyond Holmes as well. So there are other scaling relationships beyond Holmes, which isn't just sigma Tc, it might be sigma times some other variable as well. So this leads to this idea of universal scaling relationships in the context of Eliashberg theory. So any questions on Eliashberg theory? So a step beyond BCS theory by including the frequency dependence in the gap. Yes.
Yeah, so how crucial is it that you use the Einstein model here? I mean, if I wanted to replace that by the binomial, for example.
I'm going to save your question to the end because that's an extremely important question. It will be answered. But that is the main part of the talk, the importance of the Einstein model. Okay. Any other questions? In terms of Eliashberg, what I'm doing with Eliashberg theory, it's a simplest model. So it turns out we were very lucky. Because, okay, maybe I'll spoil it. The Einstein model is the only model that will lead to Holmes scaling. Okay. Any other questions? Okay. So the superfluid density for general tau and lambda. So the superfluid density in general in Eliashberg theory is given by this equation. So on the top line we have the imaginary axis, and the bottom line we have the real axis. So we see superfluid density is pi, T, so this is general temperature as well. So let's take T going to 0 for a 0 temperature. Delta omega squared plus delta squared, 1 over z square root plus 1 over 2 tau. And here it's on the real axis. So it's a real part of this integral equation here. So real axis BCS and ETH respectively, so here's the BCS form, is given by this equation. So we see pi delta naught tau, subtract this integral from delta naught to infinity. Now, in the ultra dirty limit, when delta naught tau is much smaller than 1, basically this integral doesn't come into play, and the superfluid density is pi delta naught tau. So we can reproduce someone else's result. In the clean limit, we can rigorously show that the superfluid density is 1. So basically what this is telling us is physically it's not in a clean system, basically all of the electrons are in the condensate net. NS over N is 1. While in the dirty system, it's quite small. They have an almost vanishing superfluid density. Because tau is very small. In the Eliashberg system, it's actually a little bit different now. Remember, in this context, we can take sort of a weak Eliashberg approximation here, weak-like approximation, where delta is delta 1 plus I delta 2. And now we have a similar equation, but now we have this new term, gamma, which is 1 over 2 tau z. What's interesting here, so similarly Z1 is going part Z, and we see the dirty limit, we have the exact same thing, pretty much. A pi times a gap, a tau. Whereas in the clean limit, the key here is that the superfluid density is not 1 in Eliashberg theory. It's reduced due to these strong electron-phonon strength. It goes as 1 over Z. So we seem to have this suppression of the superfluid density due to stronger electron-phonon coupling strengths in the clean limit.
So just and Z1 is
the real part of Z.
What's the real part?
Yes, sorry. Okay, so imaginary axis, we can also look at numerics to track this.
The Z had to be real.
On the imaginary axis. On the real axis, it can be.
Define Z to the imaginary, the odd part of.
In the imaginary axis. Okay. So yeah, so it will be different on the real axis. Yeah. So imaginary axis always has to be real, correct? But on the real axis, never can be.
Gamma is decoupling?
Lambda is decoupling, yes. Lambda is electron-phonon coupling.
What's gamma?
Gamma, sorry, let me go back. This is gamma? Oh, it's 1 over 2 tau z. Okay. So now, we can look at the superfluid density versus 1 over tau. So the way to read this diagram, so tau being small is going to be dirty. So 1 over something small will be huge. So here's the dirty limit, this is the clean limit. So this is numerics I did on the imaginary frequency axis. So it had nothing to do with the previous calculation, so let's check our previous calculation. So in a dirty limit, we see, now no matter what the lambda is, yeah, I did 0.7 to 100, we see that it always collapses to the same value, disappears, it goes to 0. Now in the dirty limit, in the clean limit side, recoupling, it's a little bit suppressed by 0.1. But then as I increase lambda, it goes down. So we see that this electron-phonon coupling makes the clean system act like an effective dirty system. That's like an effective diffusive mechanism.
The same limit, which is 0. Or is that not 0? Or the 0 is below that?
Sorry, what?
The 0 is below that dashed line.
No, this is the 0 line.
The 0, so it goes to 0.
In the dirty limit, yes. In the clean limit, if I went to larger lambda, it would also go to 0. So in the dirty limit, it goes to 0. In the clean limit, it's gradually going to 0 as I increase the electron-phonon coupling strength. So, sorry.
But there's also a reversal of behavior, right? So once your mass is certain amount of dirtiness, the higher lambda actually improves the density of group pairs.
Yeah, so we're not sure how we noticed that too. We noticed that's interesting, so I think you can give us like this regime, right? Yeah, so if you notice in this regime, so if I'm here, I'm sort of in between clean and dirty, and as I increase lambda, it actually increases. It increases and then decreases actually a little bit.
Right.
So it's like a sweet spot where it actually increases. So this is important because in between clean and dirty, bizarre things happen with home scaling as well. So maybe this is connected, but I'm not completely sure yet. Now, if I can plot the same data versus lambda, the electron-phonon coupling strength, and we see now the superfluid density versus lambda. Blue here is dirty, green here is clean. And what's interesting is we seem to have an upper cutoff in the superfluid density. It's no longer 1, it's decreased from that amount. And this hard dashed line is 1 over z. So we see 1 over z captures this ultra clean superfluid density. It can't get any higher than that.
So this is still Eliashberg theory.
Yes, this is Eliashberg theory assuming an Einstein model. So this, what I showed before was the theoretical work on the axis, and this is a numerical work on the imaginary axis by Eliashberg theory. So we seem to have some behavior here that works in a clean limit that's very different from the BCS system. Now, an ultra clean strong coupling limit, ns over n versus ns over n goes as 1 over z. Now, the electron-phonon coupling strength is affecting the superfluid density. It should be affecting the normal state as well if I go above Tc. So the normal state conductivity will also be affected by the electron-phonon coupling. So here f is for me the f function. Z choose the imaginary part of the renormalization on the axis. And I define chi here in a second, which takes the part of tau for strong electron-phonon coupling. So it's defined by this integral, and what's important here is that in a dirty limit, basically we lose all behavior from the electron-phonon coupling, so this reduces to tau. So we retain the normal DC conductivity, and we know in the dirty limit, due to the formula. However, in the clean limit, normally we would just have a diverge, right? Because tau will diverge, conductivity will diverge. Here, it does not. Here, we actually find it's proportional to 1 over lambda. So, due to these electron-phonon coupling, it will reduce the superfluid density in the clean limit, and it will reduce the DC conductivity in a normal state at T equals DC. So we have a T equals 0 superfluid density and a T equals DC normal state conductivity for any lambda and tau. Now we can actually look at some home scaling theoretically. Before I do that, any questions on what I just showed? Okay. So we call BCS home scaling, we had one altitude, and we found it in the dirty limit. Now we can look at it in a clean limit. So in Eliashberg theory, basically we can take the superfluid density and plot it versus sigma Tc divided by the Planck frequency squared. And we see here that this is 1 over tau being very big, so it's basically the dirty limit. And we see that we have this linear scaling relationship. Basically, we can imagine this as a single line of 3 dimensions where the color is electron-phonon coupling strength. And I project onto the Holmes axis, which is superfluid density versus sigma Tc. And we see home scaling always works in a dirty limit for these lambda values. But the important thing is that this numerics doesn't just work at some specific tau range, it doesn't just work in an ultra dirty limit. We can also consider it in arbitrary tau. So let's look at in between dirty and clean. So what I'm going to do is I'm going to make the 1 over tau gradually smaller. So I'm going to go towards the clean limit now, smoothly. So home scaling in between dirty and clean is only really valid for ultra strong and ultra weak. And go a little bit further. So this was a little bit unexpected result from the numerics, and we really don't know about this theoretically, right? Because we can often very easily take tau going to 0 or tau going to infinity when this is arbitrary tau now. So we have this bizarre bend-back behavior at intermediate tau and intermediate lambda. As I go cleaner, so home scaling, the clean limit now, is only valid at stronger coupling. And now if I increase decrease 1 over tau further, this would flatten. So basically it would flatten this down, back down. Now I can show the same data on a phase diagram, and this is what we have. So this is the numerically found Holmes phase diagram that contains all the data we just showed. So lambda is plotted on the y-axis and x-axis is 1 over tau. So here is the weak coupling regime, the lower part of the y-axis, and the stronger coupling regime is here. And this is the dirty part, and this is the clean part. So weaker coupling is the BCS theory. We found that it's the same Holmes slope we had before. Here we have no Holmes scale because the superfluid density is 1. And we see as we increase the electron-phonon coupling strength, the Holmes scaling reemerges due to this strong electron-phonon coupling strength, and we actually have this region is actually this bend-back behavior, where it's violated. And the color denotes the value of the Holmes slope. Now, and also, I won't go into this in depth, but basically there's other scaling relationships that have been proposed in the literature. One of this is Pimenov scaling, where superfluid density scales as sigma tau inverse. This was an earlier version of Holmes scaling. And it was shown to be violated in some contexts of the group rate, so it wasn't universal. But we actually find that in Eliashberg's system by just increasing electron-phonon coupling. Now, Rufus and I developed our own scaling relationship, just multiply sigma by omega e, and that is also obeyed as we increase electron-phonon coupling strength as well. So, in the context of Holmes, Pimenov, and Holstein, these scaling relationships with sigma are obeyed if we take lambda increasingly strong in a clean limit. Now, we can talk about now why are we getting this in, why are we getting Holmes scaling in the first place in this Eliashberg system as strong as coupling strength. Now, in the context of the cuprates, why were people saying that we were getting Holmes scaling in the cuprates? And one explanation of this was strange metal. Because we had a strange metal phase, people suggested there's some connection between tau and Tc. And this was known as Planckian dissipation. Now tau is inversely proportional to Tc. So we can actually plot tau that we found before for the electron versus tau Planckian, and it should saturate to about 1 when we have Planckian dissipation, and here it's not super Planckian. So by this Planckian bound. And we see this for the context of the Eliashberg theory we just considered, the same part lambda plus 1 1/2. There's no correlation between where home scale was valid and where we actually have Planckian dissipation. So that connection between Planckian dissipation and home scaling actually doesn't work in this context. So why actually is Ohm's law stored? So let's go over these 4 examples and explain why. So the superfluid density in a BCS system basically is given by this result. Now sigma Tc over the plasma frequency squared, and results in superfluid density. And if we plot it to the slope, this is about 0.885. In the ultra-clean regime, the superfluid density is about 1. In a dirty regime, we can also solve for it, and we find that it's basically the same idea. And in the dirty regime, this was stored. This is a consequence of the formula T equals 0 diamagnetic response, and sigma 1 dc equals T equals Tc. And this is discussed in the Jen's book on superconductivity. So basically, the diamagnetic response and the normal state conductivity have the same functional form. And that's why we have this similar scale relationship. Now, in a clean system, what's important here is now actually the form of Z I mentioned earlier. So superfluid density in an ultra-clean regime goes as 1 over Z, and Z goes as 1 plus square root lambda. So I here is an integral, it's a unitless integral, and that goes to 1 as I increase the electron-phonon coupling strength. So the Home slope actually goes has very weak lambda dependence. It goes to square root lambda. And that is basically the 1 over Z dependence is what leads to home scaling. And the reason why we have 1 over Z in the superfluid density is a consequence of non-Galilean invariance. So basically the work of Chubakov in 2023 showed that the superfluid density scales as 1 over Z only in the case of a non-Galilean invariant interactions. Otherwise, S over N equals 1. So non-Galilean invariant interactions in our context means Eliashberg theory with dispersionless bosons.
I'm totally confused as to why this is related to non-Galilean invariance.
So basic
Galilean invariance.
So if I have an Einstein-phonon model, there's no momentum dependence. So if I do a Galilean boost, then there's no momentum dependence, so it will look different. So sorry, if I have a
Galilean dependence is the relationship between linear dependence on time and a quadratic in momentum. So I'm not sure what you're talking about.
So the point here is that if you consider some dispersion, if you consider some boson with a dispersion, so if there's frequency dependence and there's momentum dependence,
yes,
then that system will be Galilean invariant. But if I have a dispersionless boson system as an Einstein-phonon system model, then I will have no P dependence. It's just frequency dependent. It's dispersionless.
Oh, you're defining Galilean invariance as the canonical situation in the continuum
Yes,
system.
Yes.
And you're contrasting that to you're contrasting it to just non-dispersive systems. Is that it? That's what you mean?
Yes. So I think that I'm using this terminology from, like I said, Chubakov. So let me explain what he did. Maybe that'll make a little more sense. So if we have so basically this comes from the form of the electromagnetic vertex correction.
So there are many more options between
Okay.
between Galilean and
maybe we can discuss this offline, and I can show you also the paper that actual copy uses this language. So basically, if we have some boson system with some dispersion, then with some finite dispersion, then so we will have some system, then we'll have basically this electromagnetic vertex, which will exactly cancel the 1 over z contribution of superfluid density. So the superfluid density is in perfectly 1. Sorry.
So I'm supposed to read from this.
So basically, this is in the context of the vertex fraction for a simple Einstein-phonon model. Well, now it's basically going to be R under P, and then this whole term will just be 0. So let me
It will be 0 in
Einstein model.
an Einstein model where there's just one frequency.
Yes. So there's not going to be no dependence on the frequency in the bosonic term, in the bosonic form. So if I have no momentum dependence, it's just a simple odd function of momentum.
So this is a static situation.
Yes.
Right?
Yeah. So right, this is a delta function, spectral function for the Einstein model. So
Delta function in
yes, and there's no
yeah,
dispersion.
it's just
Yeah.
constant.
So if
Yes, I mean
yeah.
that's a perfect.
Yeah, so if I have some momentum dependence in the bosonic dispersion, then that integral will no longer be 0, basically. And then Shubakov and company show that if that vertex correction is there, it will exactly cancel the 1 over z term and the superfluid density,
irrespective of the form of the.
irrespective of the form, no matter what. It will exactly cancel it. The 1 over z. So the superfluid density is then 1. Unless I have an Einstein model. Because an Einstein model, it has no dispersion. Yeah.
That's not at all obvious in this situation. Supposing that, I mean, that integral looks like it can have more complicated behavior. If I take for instance, a 4th order dispersion rather than a quadratic dispersion.
A quadratic dispersion, excuse me.
Well, it doesn't have, there are many options between 0.
Well, I think what he considered was between a dispersion less than p squared and something less than that, like the physically relevant situations for a quantum critical system.
The more relevant one, I would have thought, we need to consider something where the p squared term is absent and you begin with the p to the 4 term.
Well, what material would have that?
Well, anyone that has p squared being 0 will very likely have p to the 4 term.
I mean, I can double check that. No, but I think
I would be amazed if it doesn't.
yeah.
It's a much slower dispersion.
Mm-hmm. I mean, I can.
That's irrelevant because it's too small.
It may be, but I suspect it isn't. I suspect it.
I can double check Triple-Comp's work. Yeah, I can see if he mentioned people. Yeah.
Well, you can do the
Yeah, I can do. Yeah, sure. So the point here is that, and the way at least Triple-Comp defines this is that this is connected to at least some form of Galilean invariance, and that if we have some dispersionless boson, then this vertex correction will not lead to the cancellation. The vertex correction is 0, basically. So we attain this 1 over z form for the superfluid density.
Right.
Yeah.
P is a vector, yeah?
P is a vector and f is some function of p.
So is the right hand side a vector?
No, because no, because it's integral over p. No, I thought.
How is how
Yeah, I can double check the equation.
The equation is 0.
It was short. Yes, it's 0. It's 0 because I did a Legendre.
In overall dimensions you can see, in all directions you can see, yeah, I see that.
The integral is over the Fermi volume. It's a three-dimensional vector.
It doesn't make sense.
It's a three-dimensional integral.
So
Okay, maybe let me.
gamma's a scalar, isn't it?
Maybe the issue is
Yeah.
that there's a P times FP there, and the P is a vector, and it seems weird if you're integrating.
Yes, I can go back to this. Like I said, this is using Schumacher's
The
notation.
equation doesn't make sense.
Yes,
That's right.
I'll go over it again. So basically the point here is that, so once again, this is just using this idea of the Einstein model. And in the Einstein model, we can just expand in this form using expanding in terms of Legendre polynomials. And then that term will just be 0. Like I said, this result was just repeated from Chubukov as well. And this is just, so I can go over it and I can show you that paper later as well.
I mean, the
So,
equation is fine to me. I mean, I
Yes.
think the diagram you
Yeah.
wrote, I can now evaluate
Yes.
it very easily.
Yes,
You just go and find a diagram,
Yeah.
which is not hard to
Yeah.
evaluate.
yeah. I'll go over the paper later on to answer your question. So basically the point is that home scaling is present in the clean Eliashberg system by virtue of the superfluid density going as 1 over Z, which is specific to the Einstein model. And therefore home scaling unifies nearly all non-Galilean invariant electron-phonon superconductors. And this comes back to this idea of the Ivan Veen principle we talked about before. Non-Galilean invariant superconductors are more or less dissimilar. Non-Galilean non-invariant superconductors are more or less alike. Now finally, I just want to flash on this one thing, this last slide. So basically, I'll call that an asymptotic limit of Eliashberg theory. Now, in this context, lambda goes to infinity. So in this context, we can take the weight of the Einstein harmonic oscillator A equals lambda omega E over 2 to be a constant. And remember, we normalized all the variables by omega E squared with lambda over 2. So in asymptotic limit, usually we see universal behavior. So the Einstein model is universal, for example, asymptotic limit. We have a universal equation for TC. We call it TCAD because this is known as Allen-Dynes result. That goes to square root lambda. So in general, the home slope becomes either 0 or ill-defined and asymptotically strong in Eliashberg. And the same for these other scaling relationships coming out in Holstein that I showed. But what's interesting is that even though each one goes to 0, we can look at the ratio of the dirty to clean limit. So in the dirty over the clean limit of the superfluid density, we've seen that this is equal to pi lambda tau omega E. And if we look at either sigma Tc, sigma tau inverse, or sigma omega E for clean over dirty, we also have a similar result, and it's always 1 over lambda 3 halves times pi square root 2 a tau omega E, where a, remember, from before was about 3.9. So the ultra dirty over the ultra clean home slope, as I've been always hated here, will always be basically omega E over 2 Tc. So this is a universal result for the Eliashberg home slope.
What does AD stand for?
Allen-Dynes, it's 2 persons' names. So it was discovered in the 1980s that the TC is in this universal form. So the ultra dirty over the ultra clean home slope, Kamenov slope or Holstein slope is always 1 over 2 TC basically in unitless form. And asymptotically strong machine. So the point of this was that home scaling was originally introduced as a smoking gun for high TC cuprate superconductors. And we now know home scaling is more universal than the cuprates in high TC. But we really had no idea why this was the result. So in this context, we studied the home scaling for an example of a low TC system with strong interactions. So it wasn't BCS and it wasn't a high TC system. It was an Eliashberg system. And we found that we attain home scaling in a clean limit by virtue of this inelastic electron-phonon scattering, as opposed to elastic electron impurity scattering. And basically, as I said before, this idea of non-Galilean invariance is defined by Chubukov, results in this nearly universal behavior beyond some colloquial notion of conventionality, as previously defined. So, thank you for listening. Yes. Some questions are asked to me, yes.
So, okay, so it's important that you have this Einstein model type of behavior of phonons.
Yes.
But how, I mean, what can you say about the experimental situation? Usually we use that only as a high temperature approximation. And at low temperatures, we need to have some kind of power law of the phonons, usually T to the third or something. Sorry, K to the third, to actually make sense of the thermal behavior. So many of the superconductors you're talking about that there are low temperatures, so is there a justification from that point of view that we should be using Einstein model behavior?
So in the context of the Einstein model, if I remember correctly, I think Einstein was generally considered a good approximation for lead, but I had to double check that. In the context of whether or not for other materials, I agree it would probably be a bad approximation, but there's another approximation that has to be considered in this context. So I did not include the renormalization of the mass of the phonon, and that would require Eliashberg-Migdal. So that coupled with going beyond the Einstein model. So going beyond the Einstein model and including Eliashberg-Migdal are two steps I agree will have to be used to extend this work before we can actually apply to ballistic systems. Yes, and in the context of whole, I see what you're saying.
This is not really a material-dependent thing as much as a temperature-dependent thing. So really for lead, say Einstein model is a good approximation at high temperature because it gives you the correct number of degrees of freedom and it gives you the correct heat capacity, etc. But if you go to low temperature, what happens is that these oscillators that you're introducing these phonons, they're decoupling, they're freezing out because the temperature goes too low, below the Einstein frequency of the Einstein, the single frequency of the Einstein solid, and so freezes out, and then your capacity goes to zero too fast, as compared to what happens in a more realistic model where you have long wavelength modes that decouple much more slowly as you take the temperature to zero and are important at low temperatures, and you'd expect that to happen in any material depending on the temperature. So the real question is if you're in a temperature regime where it makes sense to just use the sort of high temperature approximation, or that it's actually important to take account of long frequency of long wavelength phonons.
Yeah, I think the Einstein, we started with the Einstein model because it was basically easiest to do and theoretically numerically. But I agree, like in most contexts, I would have to go beyond Einstein model to actually make like a realistic prediction. It includes like like a Debye model, to go beyond the Einstein model, to actually do something reasonable. Now you might ask then, well, I just said that the Einstein model is needed to actually get home scaling. But if I actually do include this renormalization of phonon mass, this might be relaxed as well, like this Eliashberg-Migdal theory. So now I might actually save home scaling for the case where I relax the Einstein model. But I will have to relax the Einstein model to add something physically relevant. Yeah. Exactly what you said. Yes.
So when you say to relax it to this, including Migdal.
Yes.
What exactly did you mean by this change in the phonon mass? Do you mean you want to make it frequency dependent?
So it's basically just a higher order diagrammatic term, I believe. I'm still looking into this, so I'm not completely familiar with it. I just completed the Eliashberg theory and I'm looking at Eliashberg-Migdal. But basically I didn't include any normalization of the phonon mass due to the electron-phonon interaction. Like Z just includes, Z is connected to the normalization of the electron mass, but the phonon mass will now be affected from this electron-phonon coupling. So Eliashberg-Migdal now is actually a step beyond conventional Eliashberg theory. And this changes the Eliashberg equations now. They're a little bit more complicated. And that will be a more physically relevant theory, basically.
You still work with the same methods. You're going to work with a more general system than the gap equation.
It'll be still an equation for gap in Z, but it's more complicated self-consistent equations now. The self-energy has a different structure. It's more complicated.
Yeah.
The phonon is now addressed.
Will you have coupling of the phonon to the barrier terminal?
Yeah. Generally, you always have this infinite system of your Dyson equations and you're just taking the gap equation as your favorite.
Yeah.
Assuming that the others are relevant. So
Yeah, but now we want to go beyond this to go actually include the Joshuah-phonon propagator. And that's the next step. And to relax the Einstein phonon condition. Any other questions?
So if I understand you correctly, you're assuming that the entire system is always falling into essentially the BCS structure.
To define BCS structure?
You've got some form of phonon of
Yes.
pair form.
Okay, so yes.
Your system is described by this gap equation and the higher
Yes.
structure form
I see.
interacting with it.
Yes, the superconducting glue is always a phonon model, basically. Yes. We actually.
Why is that a good approximation to all these higher temperature superconductors?
It's not. It's a table approximation. So this is exactly why we want to consider it. We want to find an example of home scaling, which is not a high TC system.
Oh, I see. You're not interested
Yes.
in that.
Yes. So I want to find
You're
something.
just focusing on home scaling.
Exactly. Yes. So using and this is why we want to focus on electron-phonon coupling, because we see home scaling a high TC. We see it in BCS. We want something that's neither. So that's what we want to consider in this Eliashberg theory.
But you're considering essentially BCS still.
Yes, so
It's a very mild area.
we could do something more exotic and consider quantum critical bosons and go to that, and that's another next step we want to consider. Go beyond a phonon model, but to consider something like a bosonic Green's function, which is now a power law structure. Triplekoff has considered that before as well, and consider then build Eliashberg theory on top of that. Do we get home scaling? So it's still dealing with the Eliashberg-like game, but now the bosonic mediator is no longer a phonon. So
it's still a phonon, but you're deciding that it's a different dispersion. Right?
Yeah. So it will have
rather than some other.
Well, the Green's function now has a power law.
Yeah, but that's just some non-local interaction in phonons.
Well, yes, but then everything is a phonon then.
Sorry.
But then everything would be a phonon. We could have considered some kind of.
If it's got some spin structure, it rotates in some non-trivial way.
Yeah, but yes, we can consider something of that form too. Yeah, we can just consider Eliashberg theory would work to some generalized bosonic model as well, and we can consider in that context as well. Eliashberg theory is not restricted to generally phonon-like models. So any bosonic system we could imagine. Okay. And also consider home scale in that context. Yes.
So are there any observed superconductors that do not satisfy this scale?
Okay, good question. Organic superconductors, some variants have a modified home scaling, where ns over n goes to sigma Tc to the 1.7, so 1.3. So Rufus says that that's still home scaling, you're just changing the power, it's still a relationship between superfluid density and sigma. I've actually talked to Chris Holmes about this, and he has new data that actually shows deviation for the cuprates at high doping. So it might be doping dependent. The problem is now experimental difficulties for getting to high doping and getting consistent measurements into superfluid density. So these measurements are hard. So I would say to really good experiment to see violation of home scaling is take lead and vary the purity concentration continuously for several different samples. And then basically you have a constant lambda, a constant electron-phonon coupling, and you've changed tau in it. So you should, well, it's one, actually they're doing that for few materials, because you need two knobs to turn really. So you need lambda and tau. So maybe lambda, niobium, and some compounds made from lambda niobium, and then change their taus, change the purity concentrations continuously, and then you would be able to see violation of home scaling. But the problem is you need to do so many experiments and change two separate knobs to actually see this variation. So I would say the organics and high doping cuprates would be the most likely way to see now where home scaling is violated. Any other questions?
If there's no more questions, we'll bring up Joshua again.
Who's listening then?
Stefano.
It struck the